Hello, 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 hello,
Hello.
hello, 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 good to see you all, coming, attempting to materialize, pressing wrong button, speaking out loud, uh, imitating human being, uh, oh, hello, thank you, hello, okay,
Hey, Professor, how are you?
that's so proud, good, thank you, how are you? Oh yeah.
I'm chilling. Otherwise,
What are nice people like you? Wait, hold on a second. That's very funny. What are nice people like you doing in a Zoom room like this? Okay, wait, it is good to see. Wait, am I seeing people? I think I'm seeing, I think you're hearing me. I think, okay. Yes, that's you guys, I think, right? Which is to say, hello, hello, welcome back, everybody. I don't even know what I mean by that. Thank you for the exams. I do not have them back, but I did receive them. Everybody did what they were supposed to. Well, you know who you are, but people did what they were supposed to. Thank you. I'm not, there's nothing to, I'm sure everybody did fine. I don't know that for a fact that we're not done. I don't have any grades to give back. I hope that doesn't produce anxiety, but I have no reason to believe that anything went wrong or anything, which is good. I will, so we're just going to keep going with the material. I do actually want to try to keep today conversational and like try to keep giving you points like we were doing before for participating and all that kind of stuff. I think that's working well. Excuse me, I'm also losing. But we're going to get back to, and I want to find out. Well, let me ask one question. Well, I need to get back to this business that's on the whiteboard right now. I'll make it clear. I'll try to explain it. I'll tell you what the problem is. Oh wait, I'm looking in the chat. Looking in the chat. I think. Oh, hello, hello. Right. But I want to make sure I'm not misunderstanding one thing. Lab, like Walter's, like Tuesdays. Well, I guess my direct question is, what did you do yesterday in lab, if I may ask? You could, yeah, what did you do yesterday? If anybody could tell me. Or is that's not meant to be a loaded question either. But.
We were using a circuit simulation.
Okay.
Voltage and stuff.
Okay, so you're up to that. All right, that's totally what I needed to know. That is a great answer, and that's a million points right there. Thank you. And it's a dangerous question. It's really, I think Zoom is so weird. I mean, some of this would be true even without Zoom, but like I know that even the simplest, if I just ask what you did, it could be such a loaded question, right? I mean, depending on how you answer, it could be a test of whether you were paying attention in the right way or not. But I totally did not mean it that way. And yes, you've totally just answered. All right, I didn't know if you were up to electricity or not yet. Okay. That influences how I'm going to do today, because I would like to catch up with him and be talking about the same thing as what you're thinking. Like we should be talking about the same thing in a given week. But I do need to wrap up this one topic that like appears again on the final exam, and sort of it's kind of the central topic of this physics course, which is the Doppler effect. Okay, so thank you for. I get it now. I know you were, and by the way, I know it really sucks. Well, everything sucks in the virus. I mean, the virus even sucks. And I hope everybody's okay, by the way, in all of your families. And I hope that like, no, I don't even know what I hope. But if there's one place generally where physics labs really, really do make physics a lot more real or fun or more direct, it is circuit labs. Like that's one place where labs actually are real. And it's just another example of, I know, doing labs by simulations on the computer at home. It's like, it's everything that is not what a lab is. And I apologize on behalf of the world that I know whatever you guys can take out of any of this is to your credit. I know it is really hard. And I'm still maintaining, though, if you're gutting your, the next semester is going to be grim again. If you're well, I guess maybe somebody will be graduating, but it's going to be grim again and online again and all of that, but just for whatever it's worth. And I know you just took this exam, which is not fun, but whatever it's worth, for what I can tell, as long as you're continuing to slog through as you guys are, the degree is really still worth it on the other side. I know it's a stupid thing to say, and maybe you think it's obvious that all professors think that, but I don't think it's obvious that we all think that. And your life will be better on the other side for having gone through all this. And, and you'll be back in the lab someday somehow. But anyway, so I will start talking about electricity. That'll be the next thing I'll talk about to match up with what you're doing with Walters. But first, and then we'll give back the test next week, talk about them. And hopefully they went fine, and the final will go the same way. But this, what we're on right now is this Doppler effect thing, really important topic. So, all right, that's all by way of saying what's on the board right here is a bunch of givens I would like you to write down or whatever. It's about to turn into a problem that I'm going to ask you all to solve. I think we started playing with this before we got caught up in the exam. So like it goes back, but it's all about waves. I'm going to show you how to do it and stuff, but I'm going to ask you guys to do it first. So the setup is this, okay? I know my pictures are ridiculous to follow. What I want you to imagine, or what I'm asking, what I'm trying to draw here is imagine there's a speaker, like there's a source of a wave, specifically a source of a sound wave. By source, I mean something that's like making a wave come out in all directions. Okay, in this case, a sound wave. So in fact, I should even be clear, if you look at my dumb picture, ripple, that thing with two black dots is supposed to be a speaker, like that icon. And then those ripples coming out of it are the sound waves. Now they really would be coming out in all directions, to be sure. Like they should be coming out on the left, just so you know, they should be coming out on the left of my picture as well. It's just, we're not going to care about the sound that goes off to the left. It's there, but I'm not going to ask a problem about it. So I'm leaving it out of the picture. Okay. But so there's this speaker, it's making sound. It's what we're going to call a wave source. Then we're going to imagine that there's a receiver, an ear, hearing this sound. So that's like the dumb icon is like supposed to be this ear, and the ear is receiving this sound. Okay. But now what I want you to imagine or extrapolate from the drawing is that imagine the ear is like attached to a person that's running or in a car or whatever. And that receiver is moving at some velocity relative to, as measured relative to the medium for this sound. In other words, the receiver is running through the air, or the car that the receiver is in is driving through the air. And air being the bunch of molecules through which sound ripples through. So imagine that we have a source of a wave and we have a receiver of a wave, and the receiver is moving relative to the medium for that wave. And by the way, just to be clear, or to try to be clear, imagine the source is not moving relative to the medium. In fact, I should put that in the picture to be clear. I'm saying assume, excuse me, someone is at the waiting room. Right. I'm saying assume, assume okay, that one of the givens, and I'm going to write these givens again on the next page, because I know besides the fact that this is crowded and there's a lot going on, also it is a lot of information. So I'm going to organize it differently again in another page for you, but with you. But what I am saying is we're assuming there's a source. Oh, excuse me. Actually, sorry, that was an actual error. I mean to say that's supposed to be an S. Okay. Again, I'm going to write these again on the next page. I'll try to write it bigger and neater and all that. But I would like you to try to follow whoever all you are. I'm saying, imagine we have a source of a wave, like a sound source, like a speaker, something generating the sound. And we have a receiver for that wave, a sound receiver. And what we're imagining is that the source is sitting still in air, like sitting in some room or on the road. And the receiver is moving through the air, okay? And that's what's given, that the source is sitting still in the air. The receiver is moving through the air. And in fact, in this particular case, the receiver is moving away from the source. The receiver is moving at 50 meters per second relative to the air. That's what the VRM equals 50 is trying to say. And again, whereas VSM, the velocity of the source relative to the medium, is 0. It's just sitting there. But now I'm asking you to imagine two final things about this, two more specific numbers. Imagine that the sound that's traveling the wave that's traveling is a sound wave. And of such things we know, if you're assuming that the air is at standard temperature and pressure, then I can tell you that the sound will travel through the air at 340 meters per second, approximately. But that's a real number, and it's a given in this problem. But notice what it stands for: 340 meters per second, like the speed, that's the speed of sound. What it specifically is the speed of the sound wave relative to the medium, i.e. air. It's how fast the wave is going relative to the air. All of these double subscripts are all necessary, super necessary, really, in physics, but particular to a problem like this. There are all these double subscripts, these two subscript things are containing the real information of the problem. Like, they are not a small detail, they're essential. They are all carrying the idea that velocity is always a relation between two objects. It's never just a property of one object. It's a relation between two. It's always a comparison. So each one of these is a velocity of one thing compared to another. When we say that we know the speed of some wave, like we know the speed of sound, what we mean is we know that its speed is fixed relative to the medium through which it travels. But if you do something relative to that medium, or if you do something to that medium relative to you, then you'll observe a different speed. That's what we're going to see here. But okay, so this is what the subscripts mean. I will tell you what the ultimate question is, by the way. If I'm starting to bore everybody, I'm trying to explain the problem here, Doppler effect. But I'll tell you, oh, it does say, actually, yeah. Like you could tune me out right now. I don't quite mean it. Well, I sort of do. But I mean, the problem is written, the problem is written here in red. The problem for all of us to solve. I mean, I'm going to keep talking for a while because I think it's a lot, but the problem to solve is what is F sub WR. In other words, what is the frequency of this wave as measured by the receiver? That's what we're going to be solving for. In other words, it is the sound wave. We're asking what frequency sound wave is received, is measured by the person hearing. And that means what we're really asking is what note, what pitch, what tone, sort of, excuse me, someone's here, will be heard by the receiver. That's the ultimate question of this. Again, like, if you actually, I mean, you could stop, like, I don't need to actually say anymore. I've given you enough facts written here, but I am explaining nonetheless. What I'm saying is this speaker is sending out some note. The speaker is sending out some note, a frequency, as measured by that speaker, or as measured by anybody standing along with that speaker. We're assuming that the sound wave sent out, like the given here, just pretend to color, the given here that is given is that the frequency of this wave as measured by the source, S, what's given is that it's a 500 hertz frequency. That's what's given here. I'm like just positive by the problem. Now, what does that mean in real life, by the way? What that really means is it's a sound that's a little bit above, a little bit to the right of the A that's in the middle of any piano keyboard. Like, to be literal about this, and I'll write this on the next page if I've never said this before, but like, if you can, whether if you've ever heard music, whether you actually play or you study or you know theory, if you can picture a piano at all, or a synthesizer, like a real, with 88 keys, the whites and blacks, if you can picture that at all, if you picture the A that's in the middle, like maybe C, D, E, maybe you don't, but if you picture one of the white keys that's right in the middle, and if someone happens to tell you which one's an A, the middle A of a piano, that is a 440 hertz frequency. In fact, actually, I think okay, I mean, not to be weird, but I'll write this again on the next sheet, but I'm just trying to give you perspective on stuff. I think that's like, so 440 hertz should be that. That's 440 hertz, I believe. That's a middle A. So I'm saying, let's imagine that there's some horn of a car or some speaker or whatever emitting that tone, A, okay? And it's just sitting there in the air making A. Now, anybody who is listening will receive this sound wave, and they should also receive an A, since an A was played. I'm saying, however, if someone is listening who's running away while they're listening, or running too, but if they're running, they're going to hear a different note. And it's not going to be wrong. It's not an optical illusion or an auditory illusion. They're going to hear a different note, as in they'll have a tape recorder there, could record the note, and we could come back and play it later, and it'll be a different note. They're going to receive a wave at a different frequency from the frequency that was sent, because of the fact that they're moving. That may or may not be obvious, but it's true, and it's called the Doppler effect. And that different frequency is what we're going to solve for here in this problem. I'm saying, like, the givens here are, we have sound traveling from a source to a receiver, but the receiver is moving while it tries to catch the sound, or while it catches the sound. And necessarily, therefore, the frequency of the sound that it receives will be different from the frequency that's sent. And both measurements will be correct, just correct for the different frames of reference. We are solving for the received frequency. So that's what you're all going to do. And I am going to shut up at some point and ask you to do it. But I'm just going to try to expand more on this picture right here, make it more clear what the facts of this question are. But again, these are the givens, and you guys are going to, like, based on what we know in physics, you're going to solve for FWR. But let me be clear what I'm saying here. Okay, so I'm writing this just to understand how this is going. So this is like the coding or whatever. And I'm saying the situation, well, the situation in picture here is that we have a wave being transmitted from somewhere to somewhere else, from something to something else, from a source to a receiver. But we're going to picture but we're going to picture that either the source or the receiver or both has some velocity relative to the medium of the sound wave, of the wave itself. In this case, the medium of the sound wave, in this case, air. What I'm saying is, and tell me if you want me to turn back a page. Okay, number one, I just want to say as clearly as I can, or to write if people are tuning in and out, like the concept that we're talking about here is you have a source and a receiver in two different reference frames, which really means two different velocities. I'm going to put that on the next page in the asterisk. If they're moving at two different velocities relative to the wave medium. So if you have a wave source and a wave receiver moving at two different velocities as measured by the wave medium, then the wave source and the wave receiver will measure two different wave frequencies. This is called the Doppler effect. So when a source and a receiver are not moving at the same velocity as each other, then they're not going to measure the same frequency for a given wave. Like any one given wave will be measured two different frequencies. In other words, the note I sing will not be the note you hear if you're running toward me while I sing it, or you're running away from me, or as it turns out, if I'm running toward you or running away from you. I mean, this is what we're going to find, but this is what the Doppler effect is. So this also, if I didn't say it 3 weeks ago or whatever, this is that whole thing of if you hear like an ambulance, or even just better, a car horn coming down the street, or a motorcycle horn coming down the street, and as it comes towards you and you hear one thing, and then it's going away from you and you hear something else. So that thing that you hear like that's the Doppler effect. That's what we're talking about. Now, obviously it gets all complicated by sirens having different tones and all that. And there's all different volume things that happen when cars get closer or farther from us. But that's not what I'm talking about. What I'm talking about here, that we're about to do the math of, what I'm talking about here is that depending on how fast something is coming toward you or away from you, depending on its velocity, you'll hear different frequencies. And so when something has a positive velocity toward you, you'll hear one frequency, but then when it's going away from you, like it doesn't matter how close or far, you'll hear a different frequency, that and again, I'm talking about, I mean, obviously I'm horrible like rendition of that, but I'm talking about note here. I'm not talking about volume, That's a whole other thing, but I'm talking about the tone, the pitch of something you hear is different depending on its velocity relative to you. That's the Doppler effect. That's the thing we're talking about. Now, that's the thing that the math we're going to solve for right now. Because again, I'm sort of stalling the moment where I'm just going to throw this all to you guys and ask you to do the math. But what I'm setting up again is we're saying, well, the given of this problem is this right here, but like this is a mess, I guess. I'm saying again, imagine we've got, this is supposed to be a speaker. It's like the thing on like archive.org or whatever. So this is supposed to be a speaker and it's making sound, right? Okay, and we're imagining that the velocity of the sound wave relative to the medium, okay, that's a given at 340 meters per second. Now that's a real number again. That's a little bit short of like 1,000 miles an hour. It's like 900 miles an hour. That's how fast sound is. It's pretty fast, right? Like it's so fast that it actually requires like super expensive airplanes to go that fast. But on the other hand, we do have airplanes that do go that fast, right? But they're like a big deal. Like I've never been on one, right? So I've never gone the speed of sound, but things do go the speed of sound. So it's like an interestingly high, but manageably high speed. And it's about 340 meters per second. But so it's like the speed of thunder is what we're talking about here. But what is that? That is how fast the ripples propagate through a collection of air molecules. It's like if we have air between you and me, what sound is the pulsing of the air molecules, right? Like they gather together and then they break apart. Then they gather together, they break apart, like crest, trough. It's no individual air molecule moving at all. No, right? This is a wave pulse, but the speed at which that pulse pulses through air molecules is this, like 340 meters per second. Okay, so that's the wave relative to the medium of air. That's a given in this problem because it is like known about sound. Then we're also saying, let's have a given in this problem be that the velocity of the source, relative to this medium, we're going to say is 0, i.e. the speaker is just sitting there in the air. Okay, I'm just repeating what I wrote 2 pages ago, but trying to say it clearer and whatever, but hopefully everybody's starting to see what I'm saying, because again, I'm going to let you loose on this once I think it's clear. Those two are given. So this is all givens. Another given is that this speaker that's making this sound that's escaping at these, in these ways, we're going to assume that the frequency of this wave as measured by the source or relative to the source or from the frame of reference of the source, we're assuming is like is given to be like 500 hertz. Again, that's a little, oh, so I was saying before, that's a little bit sharper than, a little bit higher in pitch and a little bit to the right of, on a piano, the middle A, okay? It's not quite a B, it's like an A sharp, like the black key, if that means anything. And again, these are real numbers. I'm doing
Bless you.
oh, thank you very much. Thank you. It's so disgusting that I'm doing them. So it's so weird.
It's okay. It's Corona time. We understand.
Okay, I'm looking for my mask. It's so weird. Like, even though I'm on the computer, I totally, what I really want to do with all you guys, what would be the money breaking, like, success story of ever for the virus? We all gotta get together and make and sell, like the scratch and sniff ebook of how to do physics, like a book that would get smells. No, I'm going to stop talking right now. I'm sorry. Like, but that's, that's the one thing that doesn't get across the internet is smell. And maybe thank God, because since everybody's having physics class and everybody else's bedroom and bathroom and beyond, but like, it is weird that the one thing you can't get across is smell. But okay, I guess that's really all right. But that's what we're really all missing. Okay, thank you, bless you too. What the heck was I saying? Okay, oh yeah. So we're assuming that this note that's being played is like a 500 hertz note. That's all a given. And what also is given is that someone's hearing this note. That's supposed to be an ear. I know. Well, actually, that's really not at all clear. Okay, now that's an ear. Okay, that has an earring. Okay, that's an ear. And that's going to hear that sound. But the one other thing that's given that makes this a Doppler effect problem is we're assuming that ear is not sitting in the air. We're assuming that it's the receiver. It has some velocity relative to the medium. And let's give it a very fast one. Like, obviously the ear is truly in a car or something. The given says that it's going at 50 meters per second. And by the way, I'm also doing something implicit and intentional with my signs, like positive and negative signs, or what appears to be none. In other words, I'm making a decision that I recommend we always make with all Doppler effect problems. In my mind, I'm going to Carolina, and in my mind, I'm saying, oh, this wave that we're looking at, this wave that's going from the speaker to the receiver, it's going from, like, on my page from the right. Yes. I think, yeah, like positive means toward, right? I think we're saying this. Yeah, that's awesome that Vicky put that. I think we're both saying the same thing, which is I'm saying whatever that wave is doing, going from the source to the receiver, that direction that on my page happens to be from left to right, and like maybe it is on your page as well. But whatever it would be, I'm calling that positive. So anything that goes in the same direction as that wave, I'm calling positive. So when I say that this ear is going 50 meters per second, I actually am setting it up to mean, 50 positive. I'm saying in this example, because we're actually going to end up doing 4 cases, to tell you the truth, 4 different examples of different combinations. We actually do have to know 4 cases of this. In this case that I'm saying, I'm assuming that the receiver's running away from the source, so moving in the same direction as the wave itself, i.e. all positive. These are deliberately positive numbers is what I'm saying, but these are all the givens. So it's like a positive number, and this is a positive number. And this is also positive. Frequencies are always positive numbers. Given all of that, the question is, the question is, and this is where I keep threatening this, but in a minute I'm going to throw it to you guys. The question is, okay, what's the frequency of the wave as measured by the receiver? What I'm claiming is it's not going to be 500. Okay, I'm going to set you guys up to do the math to find the number, to do the physics to find the number, but I'm going to tell you in advance a couple more things just to make your life more boring, or maybe even more boring. But what I want to say is this. I believe that the answer we're going to get if we do this correctly, like even before I do the math or set up any equations, I believe that the answer we're going to get is going to be a number. Actually, maybe I should ask you guys. Should I ask? Well, I'll plant the question. Maybe, oh my God. Oh, wow. I'm getting one possible answer to the whole question in the private chat. That's impressive. I'm pausing for a second. I'm almost even worrying if I've already taught this whole thing and I'm wasting everybody's time too. I don't mean to suggest that just because somebody got an answer. That's and I think the answer is right. Also, I'll say one thing. Well, okay, I'm going to say this, and that's very cool. And anybody else who wants to put anything in any chat, please do. I am impressed, and I am slightly worried that maybe if I already did all this, I don't know that means that or not. But one thing I like about the answer that I'm seeing in the private chat is that the answer I'm seeing is lower than 500. And I believe that has to be right. Like, even without doing the math in my head, I'm already saying that's cool that someone did some kind of math or something, and they got a number lower than 500. I was actually about to ask, but so I'm going to say, that's awesome. It has to be lower than 500. If you can picture, if all of you can try with me to picture the physics of this, we're saying it's like you're standing, and I do apologize, and please, someone tell me if I've already given this whole speech, and if I've already like beaten this dead horse, then please let me know. I mean, if I'm clarifying it, then I want to, but if I'm beating a dead horse and I've done it a million times, sometimes I do that, then please let me know and I'll move on to electricity. But if you're at Coney Island or Far Rockaway, also, if you can't hear me at all, I think you can, yeah, because I sneezed, right? If you're at Far Rockaway or Coney Island and waves are coming in at some frequency, like you're like, oh my God, one just hit me in the face. Oh my God, another one hit me in the face. Oh my God, another one hit me in the face. It's like 3 every second. Oh my God, they're coming in at like 3 waves per second, right? Hopefully you can imagine if you started running toward those waves, just running toward them, then they would continue to be doing what they're doing. They would continue to be just as far apart from one another as they always were. They would continue to be going the speed that they always are. But if you're now running toward them, then of course you're going to meet them more frequently than if you aren't running toward them, right? Because they're coming toward you, but at the same time you're going toward them. So there's less time between gaps. Sorry, there's less time between wave ripples that we have to wait, because while they're coming into you, if you had to wait 1 second, now you're running toward it, so you only have to wait half a second. And similarly, therefore, to come back to this problem, if you ran away from waves at Coney Island or at the beach or whatever, they would be hitting you less frequently than they were being sent out. Like, you would receive waves less frequently than they're being sent if you run away from them. And that's precisely what's happening in the problem here, which is why I totally, so far, very much like the answer that's put in the private chat. And I'm sorry if I'm boring that person, and I'm not being sarcastic. Like, I hope this is not like a total drag for that person, assuming they're right. So someone in the private chat put a number that's less than 500. And I'm already like, yeah, that's good, because it better be. We're going to receive a frequency that's less than 500. Now, how can we know what the exact number is? I think here I will turn it to everybody. So this can include or not. Like, I'm going to give you I'm going to give you maybe 3 hints. I'll tell you definitely the equations that you have to use to solve any Doppler. Like, now here's another thing. You could just look this up on the internet, like anything in the world at this point. There even is a Doppler equation that you can look up on the internet that is supposedly a shortcut to like a lot of stuff that and you can do that. And if you get the right answer, God bless. I will say that generally speaking, it's very easy to construct a Doppler effect problem where that equation that you find on the internet all of a sudden fails or doesn't make sense or is used wrong. So the method I'm about to teach everybody is a method that I would recommend more. But no matter what you're doing, I'll tell you that the equations that I use exclusively to solve any Doppler effect problem, particularly including this one, and the 2 equations I use always are ones we have in this class. Well, you can put, you'll see about the subscripts in a second. That's one. So everything we're doing is going to be, and I think we had this like drilled into us a lot a few weeks ago. The speed of any wave is its wavelength times its frequency, always true. But then what do we mean by speed? Speed, velocity is always a relation, never a property. The velocity of one thing relative to another is always equal to this is obvious, but not like everything in physics. That the velocity of me relative to the sun is equal to the velocity of me relative to Earth plus the velocity of Earth relative to the sun. Or put another way, the velocity of me relative to a subway plus the velocity of a subway relative to Manhattan gives you the velocity of me relative to Manhattan. That's why I ride subways, even though I totally don't because there's a virus, but you know what I mean. I'm saying these two equations are what I use to solve any Doppler effect problem. I'm going to, in fact, give you one more hint. I'm really amazed and psyched and impressed and trying not to ignore the fact that there is at least one answer already in the private chat. I want to verify it or not. So I don't want to keep everybody in different places, but what everybody's trying to solve for is the frequency of the wave according to the receiver. I'm saying you're somehow going to use these two equations, but I'm going to give you one more hint. I'm going to actually say the procedure, and then I'm really going to shut up. And even if one person takes over, that isn't me, that's fine. But remembering again the goal, well, I'll write this on the next page. So our goal is to solve for the frequency of the wave relative to the receiver. Okay, that's what we're solving for. Frequency as measured by receiver. What you're given is the frequency of the wave relative to the source, and among other things. You're solving for the frequency of the wave relative to the receiver. You're going to use the equations I just wrote on the other page. But to help it along a little bit more, the procedure that I recommend that you follow is as follows. Actually, I'm gonna write this whole well, I'm gonna write this on the next page. I apologize. I'm gonna write the procedure, and then but I'm gonna ask everybody to do this. And I'm gonna ask you to give me input as you're doing it. I mean, I don't think this is easy, but I am laying it out. So when you're gonna solve, you're solving for this. That's going to be everybody's goal. And again, one person has done it, and so I sort of apologize. Maybe I'm leaving that person hanging, but and maybe I'm leaving other people hanging in one way or another. Blame it on the virus. Blame it on the virus. We're solving for F sub WR, the frequency of the wave relative to the receiver. Here's the recommended procedure that I'm going to write on the next page. First, solve for the wavelength according to the source. Now, I am not going to tell you right now explicitly how. I think you can figure it. It's one of the two equations I just wrote 2 pages ago, but solve for the wavelength as measured by the source. Then, and I'm going to ask you guys to tell me what that is as we go, but then assume something that I think is true and reasonable. Assume that the wavelength according to the receiver will be the same. And this is the key to all Doppler effect problems. In all Doppler effect problems, the source and the receiver will measure 2 different frequencies. And that's in the end what happens and what we care about. But they will always measure the same wavelength. They will measure 2 different frequencies, but they'll always measure the same wavelength because if you picture like the Coney Island example, waves are rippling along. If you run into the waves or run away from the waves, hopefully you can picture what I'm saying, that given that the waves stay, given that the waves don't know what you're doing, the gap between any 2 waves is not making any reference to what you're doing. So the gaps between waves stay the same. And therefore, if you run through those gaps or run away from those gaps, you'll time your motion relative to those gaps in different ways. But the gaps will stay the same. So what I'm saying is that when the Doppler effect occurs, when frequencies are measured at two different frames of reference, what won't change is the wavelength. So the wavelength is what you solve for first, up to you. Maybe some of you have now done it, maybe not, but you do whatever one of the equations I put on the other page, solve for the wavelength according to the source, then tell yourself, oh, whatever that wavelength is according to the source, that's one thing that the receiver will agree on is that wavelength. So then using that, then the final step you'll do, and this is what you'll use, and I'm not telling you what equation or what, but use this to solve for the final answer you're looking for, which is FWR. Now, again, now I'm going to check, I'm going to shut up, I'm going to do it myself and check. There are 4 cases of what we're doing. This is the first case. Again, I'm impressed to say, or happy to say, that somebody's put an answer in the chat. I'm going to check that answer. But also what I'm saying to everybody is you're trying to ultimately get an answer for FWR, but this is the procedure. So if nothing else, please just do one step at a time. And if you understand my first step, solve for, for the wavelength, feel free to put that or anything about it in the chat or say whatever you want. But this is what we're doing. So we're doing this and this and then this. But in the meantime, I'm going to do it and check the answer that's in the, but yes, I now shut up. Excuse me, folks. Wow. Thank you. Got it. Thank you. Got it. Thank you. Got it. It smells great. Okay, got it. So I'm getting a little bit concerned, guys. So I'm returning I'm looking at your stuff while we're sitting here. I'm returning some of these participation points from last time or from the time before. I mean, I'm still owe you many points, but the points thing is still happening. I'm not trying to be weird. I'm looking at, and I apologize if in any way, any of the silence right now has anything to do with, I'm just checking something here. But I feel like what I'm asking you all right now is not, I mean, I think if anybody were focusing on it, they would have, yeah, you all totally turn it. Yes, I just want to confirm, I apologize that I don't have your exams for you yet, but it is clear that you all did totally follow instructions and turn them in. I mean, a couple of them were a little late, we could talk about, but basically they were all totally in on time and all complete and everything. And I don't think it was easy. I'm glad you got through it. I'm sorry I don't have more to say about it today. And maybe we're all exhausted, which would be understandable. But I would like some, I think what I'm asking right now is, I can't break it down much further than that. One person, well, I will say this, I totally invite the one person who, well, okay, no, that's fair. Okay, no, I'll take anything. I mean, any fee, even, I will even say this too, and thank you, Alexander. First of all, one person did put an answer in the private chat. And again, I want to say if that person wants, I think her answer is right. Oh, maybe I didn't tell her. No, I did. Yes, I did. And if she wants to share anything with the rest of the group about it, I'm all for that because her answer was right and it was good. But if she doesn't, that's fine too. But I'll say this about what Alexandra, I appreciate, like, I will take any, you know, this is tough on all of us, this whole like Zoom weirdness and blah, blah, blah. And physics is its own toughness, period. So I'll take human interaction over, I mean, even if we don't know what's going on with the question, I'll help. I just, even knowing we're out there and alive and trying or haven't walked away from our desk or fallen asleep is helpful. So like Alexandra's is helpful and there's 50 points right there. I'll say in one other class, a totally different, like in physics 203 or something this morning, people were burnt out from something else and there was a burnout, but they were still like alive and trying. We ended up sharing weird stories about from 2000 and from something else that had nothing to do with anything, which I wouldn't mind doing. Well, someone's here. But you know, just to keep us alive. But well, but I guess I'm gathering. I guess I'll go. I guess I'll. Well, I'll go a little. I mean, the problem is, well, I don't know if burnt out means. Well, I'll go further and give more answers, but then I'm going to turn it back to you guys again, just because I know me talk. Oh God. Wow. Yeah. All right. Wait. Oh, all right. Let's talk about that for a second. Let's pause, and that's fine. Let's talk about that. So I just want to have some reality. Kim, is that organic, Kim?
No, I had to because I had taken my electives first, and then now I'm finishing up my prereqs for my cell and molecular bio program. So I was just finishing up like the O3s of chem and bio.
Oh, right.
Same here for me too. I'm taking Bio 104 and microbiology at the same time with physics.
Yeah.
Oh, that's a lot, guys. Yeah, well, hopefully this isn't adding a whole, and I bet the other two are a lot more work. Yeah, you know, we
I'm
all,
really thankful for how the layout has been for this class though, because last semester for physics was a little bit stressful.
yeah, I know, and I'm sorry. And look, I could be doing more to keep us more active. I know that, but no, we don't need too much more stress in our lives. And listen, you two or anybody else who's listening right now, you know, even in the best of times when there's no virus or we're actually like going to school and doing labs, 3 science classes is a lot at once. Like I don't wish that on anybody. And I love science, obviously. Well, maybe it's not obvious, but I don't want to take 3 science classes at once. And in these conditions, I mean, no, that's rough. That is rough. Well, let me just ask, can I, okay. And so we can like, let me just ask you, is that true? The other, oh wait, so there's Vicky also, all of you are taking 3 science classes?
I'm taking 2.
Okay,
They
2.
both have labs.
They both have labs, right? Of course. And the labs, and look, we know this too. I guess I said this before. Labs, like in the best of times, even people that love, in the best of times, labs are what kill us all. We all know that. I mean, in the best of times, everybody at John Jay who's a science major of some kind or another and spending all their time in these labs while everybody else at John Jay, you know, in the criminal justice major or whatever, is like just partying 24/7. It's already really rough to be in these labs for
Oh,
hours.
no,
and
I
hours.
am taking 3. I
You're taking
forgot
3.
about one class.
Oh my God. And like, no, I do have sympathy for you guys because labs are killer as it is. They ruin everybody's lives. They go on forever, blah, blah. But at least that's where like kind of all the learning happens. I mean, in a way, you know, they're miserable, but we all kind of know that's the reality of if you like science at all, you gotta kind of like the lab in some kind of way. But then here to be doing it in Zoom is like dreadful. I mean, you have my total sympathy, all of you. To be doing science this way is the worst. Oh my God. No. Yeah, I believe it.
Yeah.
Right.
For my Bio 104, the lab is like a simulation. So it's kind of weird.
Yeah. Oh, and then there's work, right? Oh, and like I have a younger sister who went back to nursing school right before all this, and now is in nursing school, like doing like fake surgeries online. It's ridiculous. No, you guys, what you're doing is ridiculous. And obviously, I don't mean what you're doing is ridiculous, but I mean what you're being asked to do is ridiculous. And you know, you're being deprived of a lot of education that you get otherwise. Hopefully you'll still get okay grades and hopefully you get through, and sure, there will be things that you could have learned that you won't have been able, but as long as you get out on the other side and you'll still get a job and all that, and then the world, but no, I don't know how you're doing it. Oh, wait, what? Wait, I'm reading the, ugh. Yeah, and the other thing about science is, you know, you have to keep loving it to keep doing it because it is harder than everything else. And everybody knows that. Some people pretend otherwise, but oh my God, you're kidding. Yeah, we can talk about it. I don't even know. Are you serious? Wait, you're doing like simulated dissections? Wait, is that true? Yeah, I applaud you too. Wait. Well, that's fair. Okay. All right. Well, so I'm just trying to keep up here. Like, yeah, we're just taking a breather together, at least to be human. It's also helpful to me to know where you guys are at. What Alexandra just, well, first of all, I want to hear about these dissections, Kalola. I don't even know if she's being serious, but wait. Oh yeah, of course they are. No, of course they're tougher. They're tougher because they miss the whole, because they can't, because everything that's actually legitimate about a lab is exactly what's not happening online. So if you ever look, already labs are so hard for so many people, but then they get weeded out. If you're still standing in a science program, it's because somehow you learn to handle labs, which is like my hat is off to you, right? But whatever you learn to handle about labs, of course, is totally not what's happening when you're online. Of course you're dying. I mean, in the bad way, because you like the physical access isn't, wait, what, now, right, now, now as to preparing, you know, preferring this to writing and all that, like I hear you there too. I mean, certainly for me, if I'm going to sit here and do, I'd rather talk about math with you guys than talk about writing or read your work, frankly, and grade it. I mean, I hear that, but again, whatever it is, look, science is harder. I'm sorry, but your major is harder than a writing major. And we all know this. What? Yeah. Like every class that you take in science is like 2 classes. Like, and this is just true. And then if you're English and any English major friend of yours who says otherwise, like, oh no, but you guys are gifted in science and I'm gifted in this, it's all crap. Okay. Like you guys are working harder and it's just the way it is. And you might like what you're doing better, so therefore it's worth doing. And yes, but the only way you keep surviving in this ridiculous science major, because it is that hard, and I really do, all of them, CMB, I mean, I know the forensic one the best, but the CMB major, the tox major, these are hard majors to get through. The evidence for how hard they are is, every year there are some people that don't get through them. And I've given this speech before, but I don't mean to scare anybody. I always mean this as praise. You have to always remember that the reason your program is legit is because some people don't make it. And the rest of the world knows that. They'll always complain about it and blah, blah. Yeah, it's crazy. I don't know how you keep up with all this work. And some people can't, and then they don't get the degree, which means that any of you who do get the degree have proven something. I mean, it is that old joke, what do they call the person that graduates last in her class at medical school? I don't know if you know this joke, but what do you call the person who graduates last in her class from medical school? Do you know the answer? I'll say it one more time. It's a joke, but it's totally a profound joke. Well, yeah. All right. That's true. That's funny. That's good. That is Ella. Yes. But I think you might even find the real answer so I'm just going to say it again in case anybody's missed it the first time. The joke or the riddle is, what do you call the person who graduates last in her class from medical school? What do you call her? And the answer is, you call her fucking doctor. That's what you call her, because she graduated from medical school. You call her doctor. It doesn't matter that she graduated last. In fact, she gets the big prize. Maybe she got the output with the least input. I don't know. But this is true of your science degree. I'm telling you all this now, especially if you're dead or burnt out right now, or you can't do this Doppler effect thing with me. I can relate to that. I can't do it right now with you either, I guess. But let me tell you, as burnout, this major will burn everybody out, even without a virus. This major, any of the majors, CMB, any of these science majors, will cause each and every one of its people at some point to be I don't know if this is worth it anymore. You might even think, I can do this, but is it even worth it? I'm looking at all my rest of my friends not doing this kind of stuff. And the answer is yes, because if you do get to the end, then that means you got to the end of something that some people can't get to the end of. And that's the whole trick of getting to the end, is just continuing to do it, even when you don't want to. Then you get to the end and you have this degree that actually does mean something, that people actually know that you know something now, and that you know how to put up with adversity, or whatever you want to call it. Why am I even talking about this? I'm just trying to say, by the way, sympathetically, again, I think this major is all these majors are tests of inner self-discipline or whatever, which, I fail at those tests all the time. But the thing to know, the prize at the end is that the world knows that. It's why it's a worthwhile major that will get you jobs and whatnot. But why? Oh, and but it totally suffers. And even with the virus, I guess my point is, yes, it becomes an impossible major to do in the virus. It's ridiculous. Obviously, we're all just faking it in the virus. But what? Well, yeah, they'll be put in. Is that a joke? I don't even. Oh, no. Yeah, they will. Sorry, I didn't know if you were making fun of me because there barely are notes, but okay, I'm going to take that as a hint that I should get back to the Doppler effect here. But yes, the notes will be, yes, I will post everything from today, including the video. Don't forget to like and subscribe. But all right, let's, but just hang in, all of you. If you're burnt out, I do understand. And we can spend some time talking about that rather than actually do, but it's just good to know we're actually alive. Yeah. And also, have you all noticed, how about I say this too? So this virus, which sucks, no matter who you are, right? And I hope everything is as healthy as can be in your families and all that. I hope your biggest problem is your classes, honestly. But have you noticed what a crazy position, the culture of our world puts science into when a thing like this happens? Science is now black magic. I don't know if you've noticed that, but science is either science is the big savior, or it's the big enemy, or it's depending on your point of view. But it's whoever wields the science card in a situation like this with a virus wields a very, very powerful and very strangely interpreted card of black magic and sorcery, right? Because people just listen. I could go, for good or for bad, but science is elevated to great positions of bizarre authority when it comes to fighting things that nobody understands, like viruses. But okay, anyway, what the heck am I? So I'm saying this. I'm just going to start solving this problem because I am. So I'm going to do this. Okay. So I'm just saying, so I'm going to do V equals lambda F rearranged to say lambda equals V divided by F. I'm doing lambda equals V divided by F. I'm looking for lambda. I'm looking for lambda. I'm looking for lambda in all the wrong places. I'm looking for lambda because it means wavelength. It's the thing about this wave that everybody's going to agree on, whether they're sending the wave or receiving the wave. The gap between the ripples will be the same to all. So I'm solving for what that is, that gap between the ripples, the wavelength. I'm saying it's speed divided by frequency. In other words, speed equals distance divided by time. So I know the frequency, according to the source, it was given as 500 hertz. So all I need now is the velocity of the wave, according to the source. The question is, do I know that? Was that given? Well, I do know it. Strictly speaking, actually, it was not given. I'm going to be careful about that right now since I'm the one talking. But I wasn't. So on the next page, I'm saying I need this. I'm going to divide this by 500 in order to get the wavelength I'm looking for. I'm also going to turn on the light, excuse me, because I think I'm like fading in and out of. Hold on. Oh, didn't it just look like I was just walking? If you were looking at all, it looked like I was just walking on the jaywalk. Doesn't it bring you back? Yeah, no, not me either. Okay. VWS is the velocity of the wave according to the source. I need this. I need this like I need a therapist. I need this because I'm going to divide it by frequency in order to get a wavelength. Okay. Now, what I'm claiming is, in fact, I don't literally explicitly have this. I don't know literally what it is. What I know is this. I know that the speed of sound is 340 meters per second relative to air. I don't literally know the speed of sound relative to me or you or anything. I know the speed of sound relative to its medium. In order for me to know what the speed of sound is relative to you or me or anything, I'd have to know what you or I or anything was doing compared to the sound's medium. Like I'm asking here, what's the velocity of the wave relative to the source? Technically speaking, that was not given in the problem. What was given is that the velocity of the wave relative to the medium of air is 340 meters per second. What's also given in the problem is that the source, the velocity of the source relative to the medium is 0. Like the velocity of the source is nothing. The source is just sitting around in the air. So the truth is, I think I really do know what I need here. I think you guys even know it, which is why I'm being a little bit hesitant. I think VWS is actually a number that we all know, and I am going to plug it in. To what I need a second. But I think it's 340 in other words. But to be super clear how I get it is, Okay, I'm reminding us, we're doing the Doppler effect here. We're trying to analyze a wave that is traveling from one frame of reference to another. We're trying to analyze a wave that's sent from a source to a receiver, but for which the source and the receiver are in two different reference frames, like going two different velocities, observing the world from two different speeds. And the Doppler effect is what happens when a wave encounters this relative nature of speed. So I'm reminding us right here of that relative nature of velocity. I'm reminding us of, this is what I call form 4 of Galileo's principle of relativity. But this is this is how it breaks down what it's saying mathematically here. What I'm writing here is technically a reminder from Physics 101, although you might not have written it this way in Physics 101, or technically this is a reminder of an old concept, but again, you might not have seen it written this way. What I'm saying is velocity is always a relation between two objects. It is never a property of one object. So if you picture any random three objects in the world, object A, object B, and object C, like in this case, could be speaker, ear, and bunch of air molecules, but whatever, any three objects in the world. Well, the velocity of one object relative to itself, VAA, I'm looking at Roman numeral 1 here, VAA, that is always 0. The velocity of anything relative to itself, anything to itself is 0. There is no meaning to velocity when attributed to just one object in and of itself. It's meaning the velocity of a thing compared to itself is always 0. That is, I always see my nose going at 0 miles an hour away from my eyes, right? Like it's just always there. So you need two objects in order to have a velocity. That's then what Roman numeral 2 is saying. Okay, let's say you have two objects, A and B. Now we can talk velocity. If we just had one, velocity is always 0. Two objects, A and B. Okay, object A could have a velocity of 50 miles an hour to the west from the standpoint of B, from the frame of reference of B. But if object A is going 50 miles an hour to the west, according to object B, then object B is going 50 miles an hour to the east, according to object A, right? The velocity is symmetric, reciprocal this way. It's a relation between two objects. It's a symmetric relation. If I'm going east as compared to you, then you're going west as compared to me. That's what Roman numeral 2 says. That's how you deal with velocity in a situation of two objects. But now finally, Roman numeral 3, the one that we need for this Doppler effect problem, if I'm not like just going on a random frolic here. If you have three objects, A, B, and C, then there's different then velocity is a relation between two or the other, and here's how the relation among the velocity relations work. The velocity of one relative to the other can be added to the other relative to the third, and when it is, what you get is the velocity of the first relative to the third. What does this have to do? In other words, this is why you ride subways. Velocity of u relative to a subway plus velocity of subway relative to Manhattan gives you velocity of u relative to Manhattan, right? That's what this third thing is saying. I'm using this right now in the Doppler effect problem because I'm saying, oh, even if I don't explicitly know the velocity of the wave relative to the source, I do, because the velocity of the wave relative to the source will be equal to the velocity, taking into account direction, will be the velocity of the wave relative to the medium plus the velocity of the medium relative to the source. That's what I'm trying to say here. To bring it back now to the Doppler effect, A, B, and C meant any three random objects. In the case that we're talking about here, the three random objects are the source, the receiver, the speaker, the ear, and the air molecules in between. That's what we're talking about. So WS is equal to WM plus MS, just like AC is equal to AB plus BC, right? Now we know WM, that's 340. what I'm saying, and this all seems, this is all an effort to solve the frequency problem, but I'm saying we need VWS. Technically, we don't have it. Technically, what we were given was VWM, and what we can add to that is VMS in order to get VWS. So we're almost there, but then this raises the question, do we know VMS? Do we know the velocity of the medium? In other words, the velocity of the air relative to the source of this speaker. And yes, we do. In fact, I'm going to ask everybody, because I think you're going to, one way or another, I think you're going to get the question for everybody, and I'm going to shut up until someone answers this. Guys, you are killing me in the wrong way at the moment. I mean, you sort of, I'm not going to go on until I get an answer from one of you, but you're going to get the answer. You're going to get the answer because you're going to tune in just long enough to do it, because to save us all the agony, whoever you are, you will save us from this agony. Let me show you again what I'm asking. I'm asking for a velocity of v sub ms. Now, I'm going to try to explain it again, but even before I explain, I'm just going to show you something. Anybody who's paying attention, I'm going to show you the answer. In effect, we're looking for VMS. We don't have VMS. We're looking for VMS. But one thing is, if we had VSM, we could get VMS. And I think we do have VSM. I'm going to show you that again. See if you catch this. Oh, well, first of all, if we have VSM, then we just have to flip it in order to get VMS. That's what this is saying. Like we're saying, I'm saying, in fact, I'm going to say this. Like if I'm looking for the velocity, very good thought. You're totally paying attention. Thank you. I'm saying to someone who just wrote in the private chat, okay, I'm going to admit that that's not quite the answer yet. So I could say, oh, but you totally went public too, which is so great. Wow. I praise you. Seriously, Megan, I was about to praise you anyway. That was totally gutsy. And yeah, okay. And this shows we're so close because yes, I like the fact that she's taking a known number that's somewhere in the problem and putting a negative sign on it. That is the idea to do. And she went public, and I totally appreciate her guts in going public, even as I was maybe saying something was imperfect about it. But here's where we're not done. We're almost there. And again, praised be Megan. Thank you for saving me from the agony of a horrible career choice. But we do want the opposite of some given speed. We're looking for VSM. So I'm sorry, we're looking for VMS. We're looking for the opposite of some given speed. Excuse me. Hold on. I mean, either way, you could write it. This is not a mistake. I'm just trying to write. You could write it either way. But we're looking for the velocity of the medium of air relative to the source. In other words, we're looking for the opposite of the velocity of, in other words, what Megan put in the chat, which is great, is she put the velocity of the wave relative to the air. I want the velocity of the speaker relative to the air. I want how fast the speaker is cutting through the air, or put another way, well, actually what I really want is how fast the air is cutting past the speaker. But if I knew one, I would know the other. This is where Megan is right. I mean, she's saying, put a negative sign on something you know. When she hears the answer, when anybody hears the answer, excuse me, they're going to see it's even disturbingly even easier than Megan's making it sound in a way. Once you hear the answer, we're going to put a negative sign on something we know. But what is it that we know? We're looking for is the velocity of the air relative to the speaker. We don't know that, but I think we do know the velocity of the speaker relative to the air. It's given in the problem. It's given in the problem as this. It's given in the problem as this: the velocity of the speaker relative to the air. And it's not meant to be a trick, but it is easier than maybe people think. The speaker is sitting still in the air. The velocity of the speaker relative to the air is 0. Therefore, the velocity of the air relative to the speaker is ? So now I'm asking my question. So Megan's almost there, but yeah, so. We're still not there. I want the velocity. If nothing else, I mean, try to go back in the notes, everybody, and just even try to translate into English what I'm asking. Like I'm asking for the velocity of the source. No, well, sorry, no, I'm giving you that. I'm asking for the velocity of the medium relative to the source. I'm asking for the velocity of the air relative to the speaker. Like how fast is the air rushing past the speaker? Why would the air be rushing past the speaker at all? Only if or because the speaker would be moving through the air. Is the speaker moving through the air? Well, I gave the number at which it is or is not. Just look at that. In fact, it's up here at the top of the sheet. The speaker is in fact not moving through the air. The velocity of the speaker relative to the air, to the medium called air, is 0. So could someone please tell me what the velocity of the medium relative to the speaker is? And this is not meant to be a trick, but the answer will seem like a trick when someone says it, but I do need it. You'll see. Okay, what I think I'm gonna do, I'm getting a little late, what time is it? Obviously I don't want to pull teeth. I mean, I kind of do want to pull teeth, but raise your hand if you hear me speaking right now. I mean, electronically, please raise your hand if you just hear me speak. That's cool. Thank you, Samantha. I totally appreciate it. Thank you, Alexandra. I totally appreciate it. Okay, I'm gonna say it again. Just thank you, Sullivan. Oh, that was thank you, thank you. This is so like romper, but thank you. Okay, thank you, Tiffany. I totally get. I see Meg and Carol and Carolina. You're there, or any Katarina? You guys are there. Yeah. Okay, those of you.
I'm here.
Okay. All right. Cool. Okay. So, because I think we're all getting stuck here a little bit. Here's the thing. Like we all know. I mean, if we just don't know the answer, we just don't know the answer, right? But I feel like I think it may be that we're all a little bit burnt out because I feel like we're losing the thread of even what I'm asking. Because if you actually, no, for real, yeah. But I feel like guys, like yes, we're all burnt out, and I'm totally sympathetic, and this is rough for me too. I mean, it's like awkward being me, as you can imagine in this. But like. And I'm happy to do the work kind of like I'm happy to pull us along. I will do that in a minute. I'm not trying to put anybody on the spot or anything, but I think also like if everybody was actually looking at what I was doing closely enough to see, I'm not really asking anything that crazily hard. And you could ask me to back up and I happily would, but, wait, see. Okay. And you could put your hands down, I think if you, what I think I'm going to do, like to give you I'll explain the answer I'm looking for, but I feel like maybe you're not seeing the question, but I'll put down the answer and I'm going to finish what I'm doing. Since we still have time, if people are trying genuinely to get this, I'm going to finish answering the questions that I'm giving you guys. Like what I'm trying to do is solve for a frequency here. And maybe I'm also just dragging this out way too much. So I'm trying to solve for a frequency. I'm going to go back and just keep solving it and explaining what I'm doing to everybody. And I'll stop asking you. Cool. I'm just looking at you. Is that? Oh, okay. Let's see. Wait. Very cool. I'm looking in the chat. Oh, cool. Oh. Okay. Now that's very cool. Okay. Now I totally appreciate that's total points right there for Kilola. Very gutsy and very cool that she just. I opened up the link and I hope other people. And I guess I could even share this. Hold on a second. Well. Very cool, the link that Kilola just put in. And she totally gets points for that. I mean, literal points. And she'll get points for the fact that it is an image that she just shared. Now, she just shared an equation that is on the web. I want to be honest. And this is how she got it so fast before. She got an answer very fast and very correct before. Here, I will caution everybody. I am dragging this out maybe a little bit too much. And maybe I'll just finish explaining it and then turn it back to you guys. But I'm actually trying to explain a way to solve these problems that doesn't use that equation. You're welcome to use that equation. There's nothing wrong. It's true, but it's actually a lot harder to use correctly than it looks like. And we're going to look at 4 different cases, and it's hard to know how to use that different equation differently for the 4 different cases. So, but you can always use it to check, and you can always use it. If it's correct, it's correct. But what I'm showing everybody now is like the breakdown of where that equation is coming from, I guess. But that's very cool. I'm going to keep doing what I'm doing to get the frequency here. I'll stop putting it on you guys, but I will say there's 4 different cases of this. There's like receiver moving or receiver moving the other way, or source moving or source moving the other way. I'm going to finish doing this case because I do think I'm sort of killing everybody in a bad way with it. But then when I finish it and summarize it, then I'm going to say to you guys, you have to do the next two cases and just like, please do them now. Like you'll just follow the exact procedure. You won't have to think of anything original at the moment, but we will have to practice this and do it. So, okay. So I'm going to stop talking and just do it. And hopefully you're bearing with me. Hopefully you're writing this down or whatever, but I do. And yes, it certainly is a topic that Kilola looked up like that. Oh, I just lost my totally relevant to say mildly, but all right. So I'm saying this VMS equals 0. I'm saying the air is not moving at all relative to the speaker. Why? Because the speaker is not moving in the air. That was a given in this case. It's a problem. But I need this number because it's not always going to be given. You'll see in a minute. What I do with this number is I therefore say, so again, at the very least, if anybody just tells me to turn back a page, I'll at least know people are paying attention, trying. So please do tell me if you want me to turn back a page. Otherwise, I'm just going here. I'm saying, okay, we just got that because what we need is we need the velocity of the wave relative to the source. And what we're saying is that that is the velocity of the wave relative to the medium plus the velocity of the wave relative to the source. Now we have 340 meters per second plus 0 meters per second. I did all that work to get that 0, yes. So now I have this. So VWS equals 340 meters per second. That means the velocity of this sound wave, as according to the source, is 340 meters per second. Okay, as you might have just expected, because the source is just sitting there in the air, nothing special is happening. Okay, fine. So why do I care? Because that means now I can solve. I'm doing step 1 here. The wavelength of that wave equals. I'm just being consistent here. I'm saying wavelength equals velocity divided by frequency. But the velocity of the wave according to the source divided by the frequency of the wave according to the source is what's going to give me the wavelength according to the source. I'm just being consistent. That's what all these S's mean. They almost don't have to be, but I'm specifying that I'm measuring this according to the source. All right, well, VWS, we just figured out is 340 meters per second. The frequency according to the source was given to be 500 hertz. Okay, so just continuing on the next page. So so this and sorry. I want to say this. I don't know why. Why am I suddenly doubting that? Yeah, okay. I don't know why. Okay, so the wavelength of this, so what I just figured out, I'm not done with the problem. I just figured out that the wavelength of this sound, the wavelength of a 440 hertz pitch, the note a wavelength is 0.68 meters. This is a real number, by the way. Just if you're trying to picture like the world, this is a real number. Like if you play the note A on a piano, or on a guitar or whatever, you can picture it more easily on a piano, but if you play the note A or you sing the note A, what we are literally saying is you are sending air molecules into vibration cycles of 440 cycles per second. And what we're literally saying then is between each and then the air molecules start vibrating. Like, so your tongue vibrates if you're singing it. Then the air molecules like get packed together here and then they spread apart. And they're packed together here and they're spread apart. And they're packed together here and they're spread apart on their journey towards somebody's ear. We're saying between those packed together clumps of air molecules, which are like the crests of the wave, those packed together compression, high pressure packets, between one and the next is like 0.68 of a meter, like 2/3 of a meter, like 2 feet. That's long. That's freaking macroscopic. I just want you, like sound wave is a compression wave of air molecules. It's like a little earthquake of air molecules that goes from your mouth to someone's ear. And like the distance, the gaps between these clumps of air are like 2 feet long. This is totally a real thing in the real world. In other words, it's not some micro obscure phenomenon. But anyway, so we just got that the wavelength of the sound according to the source or measured by the source is 0.680 meters. Now that does not answer the problem. That answers step 1. That is step 1. Why did I get it? That's step 1. Because because the wavelength is the one thing that everybody will agree on. Like in other words, again, if here's the speaker and there's like sound coming out of it, right? And then there's this dude over here that's you or your ear or whatever. You might be running toward these wave ripples or you might be running away. as is the case in this problem. But no matter what you're doing, the ripples are a certain distance from one to the next. Everybody would agree on that distance, whatever it is. So therefore, we find it. We find that wavelength according to the source. We got 0.60 meters. Step 2 says assume that the wavelength of the wave according to the receiver is going to be the same as the wavelength according to the source. That's why we solve for the source. We can solve for the source wavelength because we have all the source information. Now we say to ourselves, aha, we got the source wavelength. Well, the one thing the source and the receiver are going to agree on is the wavelength. So we're going to shift our attention now to the receiver and say, we know the receiver's wavelength because we just stole that information from the source. We say we know the receiver's wavelength now. So step 3, we're going, and this is all much simpler once you do it on your own. Of course, I'm talking about it forever, but step 3 is we are now going to use that wavelength. We're going to use the wavelength that we just got, the wavelength according to the receiver, in order to compute, to finish this problem, to solve for the frequency of the wave according to the receiver. That's been our goal the whole time. And we're going to use this wavelength to get this frequency. How? We're just going to put it right back in the original equation we started with. This whole thing is 2 uses of 2 equations. We're going to put this back in the original equation we had, which was V equals lambda F. Originally, if you look at step 1, and this is what you're all going to do for me, and not for me, for your own education, but you're going to do this in a second in a different case. But if you look back in the case we did, we first used V equals lambda F, we rearranged it and plugged in V and F in order to get lambda. Now we're going to plug in lambda and V in order to get F. We're doing the exact same thing in reverse, only we're going to be plugging in a different V this time. In other words, we're going to say, and I can go back if you want, we're going to say F of the wave, and this is what we're solving for. This is the answer that one person did, that Kilola did, that somebody did put in the chat. But other than that, we don't know this answer yet. We're saying VFWR is going to equal VWR over lambda WR. Okay. So it almost looks like we're going in circles. We used an F and a V in order to get a lambda. Now we're using that lambda and a V in order to get an F. It seems like we're going back in circles, but we're not, because what does VWR equal? Well, I really should ask you guys this, but I really also sound like I'm doing a guilt trip, which I totally am. How do we get VWR? We're going to do the same thing we just did a second ago. We're going to say, we don't explicitly know VWR, but we know VWM. And we know VMR. Excuse me for a second. Okay. I'm going to do the same thing I did a second ago. Please, again, if you're following this at all or trying to, a step ago we did VWS equals VWM plus VMS. Now I'm saying VWR equals VWM plus VMR. I'm following the same pattern of the subscript letters. Like, it doesn't matter what the subscript letters are. They just have to be arranged in this pattern. That's what I'm saying. This is how velocity works. So I'm saying this. So I'm saying, I'm just rewriting again. Okay, I'm not going to throw this at you guys. But I'm trying to make this as clear as I can, because there is going to be time for you guys to do this exact same procedure once I'm finished with this is case one. I'm going to tell you again at the end, but I'm doing case one here. You guys are going to follow the exact same procedure and get the answer for case two. So please try to have this, what I'm saying. And this is typically a final exam problem, if that, for whatever that's worth. I mean, whatever that means. But it's like a real thing. Like it's not a toss away. But so I'm saying I'm about to follow the same procedure I just did a moment ago with the wavelengths. Like I'm about to finish the problem. I'm about to just plug in a V, divide it by a lambda in order to get an F. But how am I getting the V? Like what V do I need here? I need the velocity of the wave relative to the receiver. That's what I'm looking for, the V. Yeah, I'm sorry. I'm looking for love and all. I'm looking for this, like right here at this moment. And I'm saying to myself the exact same thing I said 2 steps ago when there was like zeros involved, but here there's no zero. I'm saying the velocity of the wave relative to the receiver, nobody ever gave me in this problem. What they gave me, what's known, is the only thing that could be known, which is the velocity of the wave relative to the medium, like that sound travels through air at 340 meters per second. And what I was told is that the receiver happens to be moving in the air. We were told that the receiver was moving through the air at 50 meters per second, positive, like in the same direction as the wave, like to the right. We were told that. Therefore, I'm saying, and you're going to use this when you do, I'm saying, therefore, I'm saying thus, this is the Megan point, which I praise again, like, and it was a gutsy point, and it was a right point, which it wasn't like fully all the way. But in other words, if we know VRM is positive 50, then what I'm saying we know is this, that VMR is negative 50. What does that mean in English? And it means that the air is moving past the receiver at 50 meters per second. Like the receiver, remember, was running away from the speaker. The speaker is running away from the speaker that way, running through the air that way. Therefore, from the receiver's point of view, if you were in a car running away from a truck, driving away from a truck, you're in the car, like you look around the car is still relative to you. Like your nose stays on your face, your car wheel stays right in front of your chest. There's your car. But you see the highway going like past you that way. And if you were zooming through the air at 50 meters per second, then what you experience is the air rushing past you in the opposite direction at 50 meters per second. That's what I'm saying right here. VMR equals negative 50 means the medium, the air, is moving past the receiver at 50 meters per second toward the speaker, right? That's what that means, right? Thus, since VWR equals VWM plus VMR, right? I'm saying that's a truism. Since that's a truism, then on the next page, I'm saying then VWR must equal 340. Well, I'm sorry, I'll write it one more time. I'm just writing the same thing again just to make sure. I'm saying VWR equals VWM plus VMR. Right, so therefore VWR equals, according to what we're saying, 340 meters per second plus minus, because we got the minus on the other page, minus 50 meters per second. So VWR equals 290. And what was the point of doing all this? The point of doing all this is we're saying in step 3, so I'm saying again, VWR equals 2, which means in English that even though sound always goes at 340 meters per second relative to air, if the air is doing something funky relative to you, or if you're doing something funky relative to the air, then sound will not go 340 relative to you. If in this case, for example, you're running away from the sound speaker at 50, then the sound is only chasing you at 290, and therefore oh yeah, and this is what Kalila put in for from the start. Okay, and this is the answer that indeed was put in from the start. And this could be gotten, I admit, I recognize, you could get this fast by plugging into the equation that Kalila provided, which is legal and fine and all that, if you know what you're doing. But I'm also, but it doesn't solve everything in the world, to put it mildly, and it doesn't help us with some other things, to put it mildly. But what I'm going to ask everybody now is, by whatever means, it could be by her means, that means, or by my means. Like, this is the answer. I'm saying that if I'm running, if I'm playing the note A and you're running away from me, or in a car driving away from me at 50 meters per second while I play that, in other words, you're running away like at 120 miles an hour, which a car can totally do. So if I'm playing the note A and you're driving away from me while I do, then you're going to hear something flatter than A. You're going to hear a lower frequency sound. If you're running toward me, you're going to hear a higher frequency sound. Right. Okay, all the above constitutes what we can call case one of the Doppler effect. Case one is the receiver recedes, meaning the receiver of the sound of the wave is going away from the source of the wave. That's the case we just analyzed. And what we find is that in fact, this one. Sorry. What we find here, just to summarize, in case one, when the receiver recedes, we find that the received frequency is smaller than the source frequency. Super important. If this is sound, it means that the received note is like flatter than or lower than the sent note. And if this is some other kind of wave, like, I don't know, like a light wave, then that would mean that the received color would be redder than the sent color, for example. That becomes very important when it comes to stars. We'll talk about, but this is what we're saying is case one. Now I'm going to turn to you. I know we have like a little bit less than a half. We have about a half hour. I'm going to turn to you guys to ask you to follow exactly the same procedure for exactly the same given numbers, but for case okay, I'm setting this up. We have limited time, but we have enough time, sadly. I'm setting up, trying to draw the exact same situation. Okay, a speaker and an ear, all the exact same numbers. Speaker sends out a sound that is a 500 hertz sound, according to the speaker. Like, same thing, sends out that A. It travels through the air, again, at 340 meters per second. So the velocity of the wave relative to the medium, again, is 340 meters per second. The frequency of the wave relative to the source is, again, 500 hertz. But this time, the one catch is that the receiver is standing still in the air, ready to receive the sound. And in this case, instead of the receiver receding, we're going to have the source receding here. The source is going away. And the question is going to be the exact, and I'm turning it to you guys, and we're just going to go to the end of the period. The question is, again, what is the frequency of the wave according to the receiver? And I'm going to tell you again, it's going to be less than 500. It's going to be like the same type of physical picture as before, like waves are approaching you, but this time, and you're standing still ready to receive the waves, but the thing that's making the waves is like a ship or something that's driving away from you while it makes the waves. Now, I will say physically the same thing's going to happen. You're going to receive waves at a lower frequency than the one at which they're sent. It's going to be lower than 500, your answer, but it's not going to be, I'm telling you right now, it's not going to be the same answer as Kalola got before, because this is now a different case, a different situation. You're going to see something different happen. But we're going to ask everybody to do, and I might actually turn off my video, I don't know. But to carry us to the end of the period, I want everybody to literally follow the same procedure I just did a second ago. And I really please everybody, do your best for this last 45 minutes. The procedure is exactly the same as before. I'll write it down again, but it's 3 steps. Find the wavelength at the source, assume that the wavelength at the source is the same as the wavelength at the receiver, then use that wavelength to calculate the frequency according to the receiver. Like, again, you could plug into the equation that Kalola provided with everybody for everybody, and I think that's great. But please do that as a check or as a double emphasis on what I want us also to do, this procedure of getting wavelength according to source, assume it's the same for the receiver, then use the wavelength at the receiver to find the frequency according to receiver. You're going to do those 3 steps. I'm going to remind you how to do them on the next page. You're going to do the same equations. So I'm going to write the procedure, but I want everybody to do it. And I'm going to shut up and we'll be done once somebody's done it. So oh, yes, great question. I did. It's not going to be the same number as before as 423, but yes, it will be. Good point. So I guess that helps with, yes.
Professor, can you go back for a second, please?
Yes, absolutely. Thank you for asking. Thank you for being alive. Yes. Is this the page or the page before? This one?
Yes, this one.
Okay, no, great. Absolutely. Oh, thank you. No, great, great. Okay, awesome. Thank you for paying attention. So I'm gonna start trying to help again, but I really don't want to talk. I really want you guys to try to get this. So I'm just gonna quietly write, try to break it down again, but I'm gonna try to not talk. And I really, and the flip side is if everybody could just fly through this, then I guess we'd be out of here earlier. But well, I don't know. But all right, here we go. Oh, yes. Yes, it is, actually. I mean, yes, Tiffany, for whatever it's, yes. Fair enough. Fair question. I would say more about that, but I feel like I shouldn't until I return the other one, but yes. Okay, just again to remind people, this is what we're doing right. Oh, thank you for reminding me. So the answer to Tiffany's question, if it wasn't clear, is yes. I mean, that's the short answer. I mean, the long answer is yes, but yes, yes, yes. And Katarina's point, fair point. I totally forgot. I guess that's Thanksgiving. Yeah, I guess that's right. If there isn't, wait, wait, are you trying to trick me? Hold on. Can I get back to you on that? Wait, is there actually school? I mean, believe me, I might cancel if I should, can't, but there, well, all right, we can pause for a second on Ekaterina's question. That's certainly a fair question, especially because I owe you. Oh, if that's true, then totally. Like, I'm so bad at picking. No, if anybody else can confirm what Ekaterina is saying, that like I'll party with you too. Okay, yeah, if that's true, I mean, I just never check. I'm always confused. But if that's true, then yeah, I'm definitely not going to go against that. Then great. That would be the first time in a while. Oh, that must be because of the virus, because it didn't used to go like that. But okay, yeah. So, and I know this is torturous, but I would like to finish this properly before we all go. So you're trying to solve for FWR, given the givens that I just wrote down here in black. What time is it? I'd like everybody to try to do it. There's a this is always on the final. This literally, this thing that we're doing right now, I promise it's always on the final. Because it actually, this thing that we're doing right now, as boring as it may seem, it's literally how we know the universe is expanding. And I'm not trying to give away anything, but really is kind of works into the punchline of the course. Like the reason we believe the universe is expanding, which is a very weird thing to believe if you really start thinking about it. Like, I don't even know what I mean, I know what it's supposed to mean, but if you really think about it, it's hard to even picture what that's supposed to mean. Like, we believe all of space is actually getting bigger and bigger every moment. Like, what is that? Like, think about that for a minute. Not just that there's becoming more and more stuff in the space, or not just that the space surrounding some bit of things is getting larger, but like, the amount of everything is getting more. I don't even like know how, you picture that, but we believe that because stars are moving away from us all the time. And the way that we know that stars are moving away from us all the time in all directions is that, I mean, not to give this away, but is that is that the color of the light that we receive is not the color of the light that was sent. There's a Doppler effect that happens with starlight. And it's why we believe in the expanding universe and believe in the Big Bang. It's like actually a big deal, I'm just saying. So it's why we're working on this. So I'm going to ask all you guys. So here are the givens. Here's the givens right here. You're solving for FWR. And I'm going to say again what the procedure is. Like the procedure, you could just plug into that equation. I don't mean to denigrate it, but you could plug into that equation that Kalola nicely provided, but you can, and that would help if people even did that now. But or you could follow the step-by-step procedure that I'm saying. I'm sort of asking you guys to plug in the number, to just continue with what I'm doing, just plug in the numbers, like find the numbers for what I'm saying here and plug them in and do it. I mean, if I get desperate, I guess I'll do it, but it would be really great. Okay, I guess for the sake of closure, I guess if I'm not going to see you guys next week, I'd like to establish some closure here. I feel terrible doing this, but I'm just going to keep going. You guys can hear me, right? You okay? I'm going to keep going. What if I like? Oh, okay, okay. Wow, you confirmed that. You definitely okay. Okay, so I'm going to just keep going with this. I'm sorry. I know this is death. Does anybody want to plug in these? Well, all right. I'm saying this. Oh, wait. Well, yeah. Tell me if you want me to go back to this page. I'll almost be shocked if you don't, but I'm saying. And tell me if you want to go back to this page. I'll almost not believe it if not. I can't imagine I'm not going to. If anybody's still paying attention, I would think that they would want me to, but Tell me if you want me to go back a page. I'm almost playing chicken here. I mean, this is almost a bluff that I'm asking somebody to call, but almost. Okay. I believe we don't, I thank you for confirming. I'm assuming the yes is in the text. Well, I'm actually not totally. I'm going to assume that Ekaterina's thing is right. And that's like largely good news that we don't have class next week. Okay, that's cool. I mean, I would try to get your exams to you anyway. I mean, I won't wait for class to get your exams to you. I mean, I have to grade them, obviously, and I'm sorry, I'm not done yet. But when I'm done, I will send them to you, you know, regardless of whether we have class or not. I don't know when that'll be. Oh, wow. Okay. Hold on one second. I'm sorry. I think this is maybe has been a tough day for everybody, or more a slog of a day. Let me just make clear again. Yeah, so I'll send you your grades, and I'm sure. Well, I hope you did fine. If we don't have class by next week, then I do have to tell you that, again, this problem that we're doing now. Like at some point, we do all have to know how to do it. There's 4 cases of it. Let me just try to say that as clearly as I can before we all go. Doppler effect has 4 basic cases. The receiver could go away, or the receiver could come toward, or the source could go away, or the source could come toward. Now, in theory, what I just did here was 2 out of the 4 cases. it's true that once you know how to do 2, it's sort of easy to do the other 2. Well, really, once you know how to do 1, in principle, you know how to do all 4. It's always the same procedure. You are going to have to know this procedure for the final exam. You you are going to have to know how to do any of the 4 cases. Like, honestly, if I were a little bit more of a certain way, I would say what you have to do on your own for home. I mean, I should say that your homework for the next class is to submit the 2 other cases and to submit all the work. Honestly, I'm not even going to say that, especially if we're not even meeting next week anyway. It's sort of, but I am saying that where we're going to pick up with electricity next time. I will at least start by just before we get to electricity and everything Walters is doing. Next time I will just pick up to remind you where we were here. Oh yeah, I'll remind you where you were here, and I'll tell you the numbers for the 2 cases. And I just have to stress again, you kind of do have to know how to do these cases for the final, because it all comes back around full circle in the universe. But the thing to notice for right now, before we go, the thing to notice is the same physical phenomenon does seem to happen, whether the receiver goes away from the source or the source goes away from the receiver. Either way, what we receive is a lower frequency from that which is sent. Either way, the logic is essentially the same. Like, you're running away from waves either way, or the waves are running away from you. But if you look closely, even if you follow the same procedure, you get an answer that's correct for either case. But you notice, please, that you do get 2 different answers for the 2 different cases. They're very similar, but they are different, and it's not a rounding thing. And the truth of the matter is, the faster the motion might be here, like if we did a number greater than 50, if the receiver were going closer to the speed of sound or the source were going closer to the speed of sound, we get even a more dramatic distinction between these 2 numbers. The fact that we get a difference whether the source moves versus whether the receiver moves is an important effect of the Doppler effect. It's not obvious, and you could only get these 2 numbers if you actually follow the whole thing. They're not sort of guessable. But all right, I'll leave it at that. I know it's, yeah, and it's rough on everybody and all that. If I could so I think you guys have been great. I think, and I owe you a lot of points and grades and stuff, and I'm sorry I talked so much at you today. If I could get any kind of goodbye, then, and I'll of course post this. I will post the notes right away, and the video, such as it was, I will post on YouTube. And don't forget to like or subscribe. But if anybody just will say goodbye or whatever, then I'll know that you heard me, and I will say goodbye as well. But I don't want to cut you off mid-sentence. So I'm good if you guys are good.
Thank you.
Oh, thank you very much. Okay, thank you guys very much. Okay, great. Awesome. Thank you. Cool. Thank you. Okay.
Bye, Professor.
Bye.
Good night, Professor.
Bye.
Bye-bye.
Bye.
Bye. I appreciate it.